So this board essentially turns its output on and off multiple times per second. This is actually a 10 kilohertz PWM generator, which means that the output of this board turns on and off 10,000 times per second, or 10,000 pulses are generated per second from this board. Now that's all very well, but it doesn't really explain how it allows us to brighten or dim our lights. So to explain that, I've drawn out a few graphs. So I've drawn out three graphs here, and what these show, on the y-axis we have voltage, so the output of this PWM board, and on the x-axis we have time. And this shows what happens to the output of this PWM board with respect to time. So we'll notice that when we measure a pulse, we measure it from what's called the rising edge. So this pulse comes along here, then it rises up, goes along, drops down, goes along, rises up, goes along. So we're measuring from this point here, the rising edge, to this point here. And because this board operates at 10 kilohertz, this here is 1/10,000th of a second. And you'll notice that for all three of the plots, the pulse is always exactly the same length. So if the pulses are the same length, how are we raising or lowering the brightness of the bulbs? Well, whilst the length of the pulse is the same, what you notice is that the time that the output is on varies. So in this example here, we can see that the output is on for about 25% of the time. So it turns on for 25% of the time, then it turns off for 75% of the time, then it turns on again for 25% of the time, then it turns off again for 75% of the time. In this example, it's on for 50% of the time, and then off for 50% of the time, and then on for 50% and then off. And then this final example, it's on for 75% of the time, and then off for 25%. On for 75, off for 25. Now, because this is operating at 10,000 kilohertz, it's far too fast for the human eye to actually see this light turning on and off, on and off, on and off. So what our brain does is it stitches them together, stitches all these fragments of images together. And what it results in is, in this example, our eyes would see the bulbs looking relatively dim because they're only on for 25% of the time that our eyes are actually seeing them. When the board is outputting this, the LEDs will actually appear brighter because our eyes are seeing that they're actually on for 50% of the time. So to our eyes, it looks like the bulbs are brighter. And here, because the bulbs are on 75% of the time, again, it appears that they are brighter. In reality, they're not, they're just turning on and off. But our eyes can't see quickly enough to distinguish that. So our brain stitches the images together and concludes that this is relatively dim, this is slightly brighter, and this is very bright. So that, in essence, is what pulse width modulation is all about. What we're doing is we're modifying the width of the pulses within this waveform. So what this relies on is a phenomenon called persistence of vision. And persistence of vision is essentially, it's your brain seeing something for longer than it actually exists for. So have you ever done that thing where you have a notebook and on a page you draw a stick figure, and on the next page you draw a stick figure in a slightly different position, and on the next page you do it again. And then when you move the pages like this, what is actually there is a series of stationary images. But what your brain sees is a stick figure moving. And that's what persistence of vision is. And there's exactly the same thing with this PWM signal. What is actually happening and what your brain sees are two quite different things, but it's happening too fast for your brain to make sense of it. So you join me at a critical moment. I've just plumbed in my PWM generator. I've not neatened up the wiring or anything yet, that's to come later. But what you can see is that, as we would hope, it gives me dominion over the brightness of my lights, which is Lovely, just what we want. So really now it's a case of doing a little bit of fine tuning and tweaking to get the lights as I want them. So for that I need to turn off all the lights in the room and just do a bit of fiddling really. Okay, here we are. Let's just see what we're getting. That's probably quite decent there. See, that gives me enough light to show that the lights are there. It's obvious that they are on and that they're, you know, in view and so on. But what it's not doing is it's not sort of flooding the deck with lights. What I'll do, it's still quite light outside, so I'll wait till it's completely dark and then I'll take another video to show you exactly what this looks like. Do bear in mind, it's very tricky with the camera on to give you a genuine sense of how bright these lights are. The strip of lights here is nowhere near as bright as it appears on the camera, but it's just the way the camera captures the light, so there's not much I can do about it, I'm afraid. Right, here we are. As we can see, the lighting is quite reduced now. Trying to get deck lights in view. There we go, you can just see one. Unfortunately, the camera still insists on making things look brighter than they actually are, but you're just going to have to take my word for it that the lights are now significantly reduced in comparison to what they were before. What I'll do is I'll see if I can take some photos which show it a bit more as it truly is. But anyway, in essence, this PWM has reduced the brightness of the ship massively. So what I've done is I've taken a few photos which seem to sort of show up a little bit better what the lighting looks like when the model is in front of you. These certainly are a bit more representative of what the model looks like than the video. And that's probably just because my camera's not good enough. So I appreciate I haven't yet shown you how I actually wired up the PWM generator. That's because I'm going to show you it in the next part of the video. So the next part of the video is me going into detail on how my lighting circuit works. And in that, I will show you exactly how the PWM generator works. So let's crack on with that. Right, so before we get cracking, I'm just going to pour myself a cup of tea. And that is the most anemic tea I've ever seen. There we go. Excellent, right, let's crack on. So, for mocking up the LED lighting circuit, what we're going to use is this. This is a battery, same battery that I use on my model Titanic, and for the purposes of the video, this represents the power supply that my lighting circuit would get from the ship. Just a battery, simple as that. Next, we have some of this stuff. This is LED lighting strip, and I use this stuff on my model Titanic for large areas of lighting. The hull is lit with this stuff, and also larger areas of the superstructure. It's just in a self-adhesive strip with LEDs inside it. Next, we'll be using some of these. These are the tiny little LEDs that I use for my deck lighting, that kind of stuff. We'll also be using one of these. This is a 330 ohm resistor. We can tell because it's got an orange band, then an orange band, then a brown band. The orange means a 3, so you've got 3, 3, and then the last band refers to the number of zeros you have, and brown means 1, so you've got 3, 3, and with the 1 0, so 330. That's that. Then we also have a fuse holder. Go into more on that later. We've got the power supply that I made in a previous video. And lastly, we have the PWM board that I've already shown you in this video. So, with all of these things, we shall make a simplified lighting circuit. So we're going to start with the LED strip. This is the easiest thing to get going. This is 12 volt LED strip. You can just see there it says DC 12 volts, direct current 12 volts. This runs off 12 volts, and just to prove it, I'm going to connect the wires up, if they reach, to my 12 volt battery, and hunky-dory, the lights turn on. Simple. And the lovely thing about LED strip is it's completely self-contained. You don't need any other components. The resistors are already installed, the LEDs are already installed. It is very much a plug-and-play device. So first off, we'll get our PWM signal generator in the path. So what we do is this is going to go directly before our LED strip. And this is, well, it's actually quite complicated, but we don't need to worry about that. All we have to do is connect the power going in. I almost dropped it. What we have to do is connect the power going in here in these terminals and the power going out in these terminals. So I'll do the power going out. This is the power going out to the LED strip. So positive, which is red, goes in here. Lovely job. And then 0 volts, or black, goes into the other terminal. Nice and simple. Before we go any further, to prove that this actually works, I'm going to plug in the PWM generator into my battery, okay? And we're going to see exactly what happens. So, let's get the 0 volt line on first. So, take a wire from your battery and plug it into the 0 volt line of the PWM generator and tighten the terminal. So far, so simple. Now, so at this point, I'm just going to turn everything on and I'm going to use my PWM generator just to prove to you that this does work at this stage. So what I've done is I've connected a 0 volt line up to the 0 volt input on my PWM generator. Then I'm going to do the same thing with a plus volts lead. So that goes into the plus volts input of my PWM generator. And then when I connect the battery up, nothing will happen because the PWM generator is not turned on. Now, when I twist the button, we can see that the LEDs turn on and I have control over their brightness thanks to that lovely persistence of vision that we were talking about earlier. So, this is a very rudimentary, but nonetheless, a functional lighting circuit. We'll now go into the other things that I add to make my circuit slightly more intelligent, I suppose. One thing I should say before I forget is don't forget to add a fuse. The amount of times I've seen people not add fuses into circuits, it's very silly. I had one person once tell me, oh, I don't use a fuse because they always blow and then it stops working. You're sort of missing the point. The point of a fuse is to break under certain conditions. It's what we call a sacrificial component. A fuse is designed to break the flow of current when there's a fault in the circuit. So if, for example, I connected this terminal of the battery up to that terminal of the battery, loads and loads and loads of current would flow. And if it wasn't protected by a fuse, what would eventually something would melt or something would break. Probably the thing connecting the two poles of the battery would melt. And I mean melt. I have seen 70 square mil wire, cable I should say, melt when someone's connected a battery up the wrong way. It's scary how much power even a small battery like this can kick out when you give it the opportunity. A fuse is designed to melt when that sort of thing happens, and it stops the flow of current, stops that fault happening. Essentially what this does is it breaks to stop a more expensive component breaking instead. So if you've got a fancy PWM generator, something like that, this fuse would break instead of something on this board breaking. So you lose a 5-10 pence component rather than a £3 component. So the next thing we're going to do is we're going to connect some LEDs. What I'm going to do is I'm going to do one string. So what we need is 4 of these LEDs. There we go. So what we're going to do is we're going to get 4 of these LEDs together in a string. Okay, so what we're going to do is we're going to solder them together. What I tend to do, this can be quite a fiddly process, so what I tend to do is I tend to tie a knot between the two LEDs that I'm trying to join. And then what I can do is I can simply solder this, and the heat of the solder melts the insulation of the wire and combines the wires together. Gives us a nice soldered joint. So that's what I'm going to do now. Let's zoom in a wee bit. Right. So I'm just going to hold the soldering iron, melt a little bit of solder. You can see that insulation is already melting. That's probably us, actually. Yeah. There we are. That's the first of our LEDs joined together. So we'll repeat the process with the others. So same thing again, we're going to tie a knot in between one LED's wire and the next one. Red wire goes to a black wire. That's another knot. On to time lapse now, and just soldering the remaining 3 LEDs into the chain. So now what we have is a chain of 4 LEDs in a row. It's quite long because I haven't trimmed off any of the wires, but here it is. Here is the first LED. There's the second. What's that? There is the third. And finally, there is the fourth, if it'll ever go in focus. There's the fourth. So, 4 LEDs in a row. The last thing that we need to do before we can connect any power is we need to put what's called a protection resistor in the path. What this does is it just regulates the amount of current that goes through the LEDs, which is of course a good thing. What I tend to do is I just roll some of the LED wire around the leg of the LED as such. There you go. We'll just solder this in place now. Same principle, the heat of the soldering iron will just melt off any insulation. Incidentally, by the way, it doesn't matter what order, where in the chain the resistor goes. It doesn't make any difference at all. The LED can go at the start, it can go at the end, it can go in the middle, doesn't matter. So we now got the resistor in place. And just to prove once again that everything works before I connect it all up to other stuff, I'll connect it into my battery. So 4 LEDs in a chain, 0 goes onto the 0 part of the battery, positive onto the positive, and there we have, typically it's not in focus, but we have 4 LEDs turning on, you can see them. Okay, 4 LEDs turning on. So we know they work. Now, this is all I've done for every single one of the deck lighting LEDs on my model. Yes, the wires get trimmed, yes, they get put into smaller spaces, but this is the exact same principle. Every single one of the deck lights starts with a resistor, then it's just a long chain of 4 LEDs which then goes back to 0 volts. That is the same process, and it's just copy paste, copy paste, copy paste. This is all that the lighting circuit boils down to. So how do we connect the LED string into my LED strip? Well, as you can see, along the strip there are various different copper pads. They go along at sort of, you have 3 LEDs in a row, then you have a set of copper pads, and you have another 3 LEDs, copper pads. And what we can do is we can actually connect our LED string onto one of these pads, because these pads are actually just replicated terminals from the batteries. So I start by cleaning off the pads using my soldering iron and a bit of solder. So just do that now. Scraping the pad with my soldering iron, and that tends to expose some bare copper. There we go. There we go. You see the solder's now starting to stick. So what I'm going to do on these pads, it actually says plus and minus. You can see there's a plus and a minus, and on every single pad, plus, minus. So what I'm going to do is I'm going to connect the positive end of my LED string. That's the one with the red wire at the end of it, which also happens to have my resistor. I'll connect that onto the positive end of the LED strip. And I'll connect the negative end, that's the other end of my LED string, onto the other side. There we are. All done. So I'll just turn this on now, and we should see everything work. There we are. And you can see that the PWM gives me dominion over how bright these lights are, just as I would like it to. But we can see that we've got a string of LEDs connected up into my LED strip. And as I say, it is really that simple. If I wanted to add more strings of LEDs, I could do. Just copy exactly the same thing again. Resistor, 4 LEDs, and then solder it onto your LED strip. And you could connect it there if you wanted, or if it's more convenient, you could connect it there, you could connect it there. Just copy, paste, copy, paste. Similarly, if I want to have more LED strip, just run some wires and connect the positive to the positive, negative to the negative, and it'll work just fine. So the next thing we're going to do is we're going to add the power supply board. Now, this is a board that just limits the voltage that comes from the battery. These batteries kick out about 12 volts. When they're fully charged, they might be up a bit higher than that, around sort of 12.56, whatever. What this board does is it takes that 12 volts and it regulates it down to about 11.1. And there is a reason for that I'll go into in a bit more detail in a second. But what's good about this is almost irrespective of what the battery gives us, if it's fully charged and it's giving us 13 volts, if it's almost empty and it's only giving us 11.5 volts, this will always kick out the same voltage, which just stabilizes the power you have going to your LEDs, which is always a good thing. So now what we're going to do is we're going to connect up my power supply board, and in fact I've already done it, but I'll show you what's going on. So for reference, I built this in episode 45, so if you're interested in how to make it, watch that episode. It says exactly how to make this board. But as I say, what this does is it takes the battery power, smooths it out, conditions it, and then sends conditioned power to my PWM over there. There are 3 wires on this. The green wire is the incoming power from the battery. The red wire is the outgoing power to whatever you're powering. The black wire is just a common ground between the two. So to prove that this is actually doing something, I'll just show you my multimeter. And this is measuring volts here. So at the moment, I'll try to get my hands out of the way so you can see what's going on. Right, so measuring across my battery, there we have 12.95 volts. Now if I measure what's actually going into the PWM, 12.36, you can see that that power supply is chopping off a reasonable amount of the voltage. Sorry, my probe just slipped off the metal there, which is why it went back down to 0 volts. So you can see that the power supply is doing something. So that power supply is now wired in between the battery and my PWM signal generator. Now, why do I need it? Well, it all comes down really to a few different things. Firstly, batteries are very good at giving you stable voltage, but what can sometimes happen if you pull a lot of current from them instantaneously, their voltage can dip slightly. And it's not an uncommon thing. If you've ever seen a car turning its engine on when the headlights are running, you'll see that the headlights dim as the engine turns on, and that's because the battery's pumping out loads of current getting the engine going. The same thing would happen if I was using all of my propellers. The battery would be giving out loads of current, its voltage would dip, therefore the voltage that the lights see would dip. And I don't really want the voltage, the brightness of these lights to dip and flicker as the ship's sailing along. That wouldn't look particularly good. The other thing is that LEDs, as with all components, have a expected life. And there's a strong correlation between the amount of voltage they see and how long they will last. So for example, these tiddlers, these can accept anywhere between 2.8 and 3.5 volts. So when I have 4 in a string, you take your supply voltage and divide it by 4, and that's what voltage they get. So if I'm getting 12 volts out of the power supply, each one of these will see 3 volts, so comfortably within their range. But obviously I've got the resistor in there, which uses up a bit of voltage, so they'll actually see slightly under 3 volts. And that's the reason why I have that power supply as well, because it just regulates the voltage. And what I can do is I can make sure that the LEDs are seeing the lower side of their voltage, which means they will last longer, which means I don't have to take the model apart regularly to change LEDs out and stuff like that. The longer they last, the easier it is to keep the model going, really. So that's why the power supply is in the way. So just to reiterate, we've got battery, then the power supply, then the PWM generator, and that's the full lighting circuit now.